You know, we tend to think of the laws of physics as these unshakable rules of the universe, right? But what happens when our technology gets so advanced that it starts pushing those laws into a corner? That's when things get really weird and honestly, really interesting.
So today, we're going to put a law you probably learned back in high school science class on trial. It's a cornerstone of physics, over 200 years old, and we're going to ask a simple question. In the face of our most extreme, cutting-edge tech, does it still actually work?
And our story starts somewhere pretty unexpected, inside a hard drive, maybe even the one in your computer. We're talking about the latest generation, which uses something called heat-assisted magnetic recording, or HAMR for short. And the conditions inside are just brutal. The pressures are over 50 times what we're breathing right now, and the temperatures can get hot enough to melt lead. It's a seriously hostile environment.
Now, to understand what's going on in that tiny, tiny space, we need to talk about the law that's supposed to be in charge, the one and only ideal gas law.
Yep, that one. PV equals nRT. I bet you've seen that before. It's this beautiful, simple formula from the 1800s that neatly connects a gas's pressure, volume, and temperature. And for 2 centuries, it's been an amazing tool. But that simplicity comes at a cost. It has to make a few assumptions about how gases behave, assumptions that, in the real world, aren't always true.
And this right here, this gets to the heart of it. On the left, you've got the ideal world. It's a perfect little sandbox where gas molecules are just tiny dots bouncing around with no size, and they never stick to each other. But then, you've got the real world on the right. It's messy. Real molecules have size, they take up space, and they definitely interact. They can attract and repel each other. Now, for most everyday stuff, the ideal model is close enough. But the inside of that hard drive, that is anything but everyday.
So let's head back to our first piece of evidence. How does this ideal law actually hold up inside that very real, very extreme hard drive?
So just to recap, inside these HAMR drives, you've got a laser that's blasting a microscopic spot on the disk to write data. And that's what creates this insane, high-pressure, high-temperature little bubble. It is the perfect stress test for our 200-year-old law.
And here's what it looks like when a physical law starts to bend under pressure. The dots on this graph, that's what's really happening in the experiment. That's the ground truth. The lines, that's what the old ideal law predicts should happen. And that gap between them, that's the breakdown. That's reality telling our simple model that it's missing something.
But here's the twist. This is what's so cool about the hard drive study. At normal room temperature, yeah, the predictions were pretty far off. But once you crank the heat up to the crazy levels inside the HAMR drive, the real-world results were actually surprisingly close. Less than 10% off from the ideal prediction. So in this very specific, very extreme case, the law bent, for sure, but it didn't really break. Turns out all that heat was actually making the gas act more ideally.
Okay, so the law can bend. But what does it take to make it completely shatter? For our second case, we need to find a situation so extreme, so chaotic, that the old rules just get thrown out the window. Let's talk about shock waves.
So imagine this. You have a tube, and it's filled with a mix of 2 totally different gases. One is super, super heavy, and the other is incredibly light. Now, what do you think happens when we fire a shock wave through that mixture at faster than the speed of sound?
This happens. I mean, just look at this graph. The black symbols, that's what the experiment actually measured. The blue and red lines, that's what our classic laws predicted. It's not just off by a little bit, it's a complete and total failure. This isn't the law bending anymore, this is the law completely breaking apart.
So why? Why did it fail so spectacularly? It really comes down to this one number, 36.5. That is how many times heavier one of the gas molecules in the mix was compared to the other one.
Okay, think about it like this. The shock wave is like a giant wooden plank suddenly slamming into a room that's just full of bowling balls and ping pong balls all mixed together. Are they all going to move the same way? No way. The ping pong balls are going to zip out of the way almost instantly, right? But the heavy bowling balls, they're going to take a lot longer to get moving.
And that is exactly what's happening on a molecular level. This is the why behind the failure. The superlight helium molecules react to that shockwave almost instantly, but the heavyweight molecules are still kind of lumbering along, taking forever to catch up. The old laws just assume everything settles down at the same time, but in this kind of microscopic chaos, that assumption just completely falls apart.
Now this might sound like a bad thing, our trusted laws failing us, but actually these moments, these breaking points, are probably the most important moments in all of science and engineering.
The legendary physicist Richard Feynman put it perfectly.
He said the real key to understanding how things work isn't just looking at the simple, neat, and tidy examples. It's digging into the messy, complicated ones, like our hard drive and our shockwave, where our models finally break down and show us something deeper about reality.
And that, right there, is the engine of progress. You start with a model of reality, a law. Then our technology pushes that model to its absolute limits until we find where it breaks. And by studying why it breaks, we get the insights that lead to the next huge innovation. That's how we build better data storage. That's how we design hypersonic aircraft. We learn from the failures. It all shows us that these laws of physics aren't really unbreakable truths carved in stone. They're more like maps, and finding the edge of the map is the only way we can figure out what lies beyond. Which really makes you wonder, what other fundamental laws are just sitting there, waiting for the right piece of technology to come along and show us their breaking point?